Awesome. Okay, so it's a very great pleasure to get to introduce Monika Schleier-Smith as our last colloquial speaker for this semester. So Monika got a AB magna cum laude in physics, chemistry, and mathematics from Harvard in 2005. She then went down the road to MIT and got her PhD in 2011 under Vladan Vuletic on cavity-enabled spin squeezing for a quantum-enhanced atomic clock. And for that work, she was awarded a Hertz Doctoral Thesis Prize. She then spent 2 years at the Max Planck Institute for Quantum Optics and LMU in Munich before joining Stanford as an assistant professor in 2013. She then became an associate professor in 2019. And that is what she is today. So her long list of awards and prizes is much too long for me to go through. But in particular, last year, she received a MacArthur Fellowship, commonly known as the Genius Award. And she recently received the II Rabi Prize in Atomic, Molecular, and Optical Physics. So as I say, it's a very great pleasure to have Monika talk to us about atoms interlinked by light, programmable interactions, and emergent geometry.
Thanks so much, Jeff, for the invitation to be, I guess, virtually on the other side of the bay today. Indeed, the title of my talk is Atoms Interlinked by Light, Programmable Interactions and Emergent Geometry. And it's a talk about some work we are doing in my group at Stanford on advancing control over interactions between laser-cooled atoms. And so I just thought I would start by saying a few words about what it is that we love about working with systems of laser-cooled atoms, really as model systems for studying quantum mechanics. Particularly over the past few years, these systems have gotten to the point where there's really an extraordinary level of, on the one hand, single atom control, the ability to detect individual atoms. These are some pictures here of from a variety of different labs of individual atoms trapped each at the focus of a laser beam. And at the same time, there's control of individual particles, but at the same time, a high degree of scalability, where this level of control can be extended to hundreds or more. And that is being explored for a number of different sort of spheres of application. On the one hand, the fact that, for example, every cesium atom is the same as every other cesium atom is the reason why we define the second, or measure of time, in terms of the transition frequency in an atom. And so these laser-cooled atoms form extraordinarily precise clocks that are applied towards also tests of fundamental physics. The level of control that I've shown on the left here is being explored because of this level of control, atoms are being explored as the building blocks of potential quantum computers. But perhaps a nearer term direction than building a universal quantum computer that is widely being explored is, can these systems be used, perhaps not to solve every computational problem, but to solve certain classes of problems, for example, from materials science, where atoms can mimic, let's say, electrons in the solid state, and one can build simple models that might capture the essential physics of anything from perhaps a superconductor to the magnetic properties of materials. And so that direction is known as simulation. So particularly for these directions in computation and simulation, one key ingredient of the toolbox that I haven't shown yet is that there's also the ability to generate interactions between these atoms. And there are a few different ways of doing that. So one approach that is increasingly widely explored is, for example, to take ground state atoms, but excite their electrons to Rydberg states, which are highly polarizable and can generate interactions on the scale of several microns. Or alternatively, if atoms are in their ground states, they can interact if they're, for example, sitting practically on top of each other within an individual well of a standing wave formed by light. So those would be called contact interactions. So here's an example where, by virtue of those direct interactions, atoms with two internal states have formed themselves into some sort of a checkerboard pattern. So these are a few pictures kind of illustrating that these are systems where one has single particle control, some control of the interactions. One limitation, though, in experiments to date has to do with the connectivity of the interactions. So atoms, and quite generally in nature, interactions tend to decay with distance. Atoms will talk to other atoms that are near them, or perhaps sitting in the same lattice site in a picture like the one I've shown here. And one of the things that we're particularly interested in my lab is sort of expanding control over the connectivity of interactions. So why does connectivity matter? So here's sort of a classical example, the internet, right? If you have sort of the fact that anybody can talk almost instantaneously to anybody else in the world with the internet is important actually to the way that information flows in the modern world, right? So somehow in the olden days, news traveled from neighbor to neighbor. Common wisdom was perhaps shared by people who lived close to each other. But these days, this is actually particularly brought home to me by this pandemic. My interactions are sort of with some network of physicists spread across the globe, thanks to this connectivity provided by the internet. And that changes the way that collaborations form and collective wisdom develops. So that's a classical example, but in quantum systems, connectivity also matters. So here's sort of two examples of ways that some collection of qubits might be connected to each other. So for example, if I have in principle some lattice of qubits that interact if they're on neighboring sites, in principle this form of interaction actually gives rise naturally to something known as a cluster state, which is a resource for universal quantum computation. If you can make this state, that's a starting point for a certain type of computation. If you have the same form of interaction, but everybody talks to everybody instead of neighbors talking to each other on a lattice, it turns out that that naturally gives rise to a particular class of quantum states known as squeeze states that are resources for enhanced sensing. And you could imagine then, or we would love to be able to explore, perhaps if we could make other graphs of interactions, maybe that would open up new opportunities. And in particular, a reason why we might expect that to open up new opportunities is that the structure of interactions actually dictates the way in which quantum correlations or entanglement forms in the system. Okay, so this entanglement, this is perhaps a bit jargony. I think in this audience, most people are familiar with this concept. But just for fun, I thought, and for anybody who isn't, I would share my 1.5-minute introduction to entanglement. What do I mean by that? So I was fortunate recently to have actually the assistance of a professional animator animating my explanation of what do I mean by entanglement. So here we go. The simplest quantum system is a quantum bit, which, like a classical bit, can be in the 0 state or the 1 state. The remarkable thing about a quantum bit is that it doesn't need to be in just the 0 state or the 1 state. It can be in what's called a superposition of the two. Fundamentally, it's unknown and unknowable whether the qubit is in the 0 state or the 1 state until a measurement is performed. And when the measurement is performed, it's almost like it has to decide. So I like to use kind of the analogy of a coin, right? A coin is a system with two states, heads and tails. And the superposition is a little bit like a coin that's floating in midair and it hasn't decided whether it's going to land heads or tail. So now the really neat thing, though, is that in a quantum system, you can have a phenomenon that's equivalent to me tossing a coin and you tossing a coin, and we repeat this experiment 100 times. And every time I get heads, you get heads. And every time I get tails, you get tails. But if I look at my tosses alone, the outcome always looks flat random. So there's this randomness, but there are correlations in the randomness. And that tells us that there's some information that I don't have. My coin toss looks random. You don't have it. But when we compare notes, there's actually some information there and not just randomness. So this idea of having information that's encoded in correlations, this is known as entanglement. And this is really the key resource for quantum technologies. Okay, so this is a key resource, and making that resource and controlling the structure of these correlations really requires some control over the structure of interactions in our quantum system. And so the dream that I've had for a while is to have something like a function generator for controlling the interactions between cold atoms, where I could realize something simple like nearest neighbor interactions, but perhaps also some more exotic structures of interactions. And the idea of sort of a function generator might sound a little bit extreme, but actually the level of programmability that's been achieved in these cold atom systems already is actually quite astounding. And I've showed you these pictures earlier of the ability to position individual atoms using laser light, right? And so this programmability of the positions is really thanks to the fact that we have good control over light. And so one thing we've been working on in my group is asking, can we use that high degree of control over light to control not just the positions, but also actually the interactions between these atoms? And in particular, a goal is to be able to have interactions that are long-ranged compared to sort of the characteristic length scale on which one can image and address the atoms, which is the micron scale set by the wavelength of light. Broadly speaking, in my group, we actually explore kind of two different approaches. One that I touched on earlier are van der Waals interactions between Rydberg atoms, where the electron is highly excited. Those can be on the several micron scale, but they're still local in the sense of decaying with distance. They don't give you this sort of connectivity of the internet where anybody can talk to anybody. So the other type of system, and the one I'll focus on today, is one where actually we have really highly non-local interactions. Any atom can talk to any other. And the way that we achieve that is by allowing the atoms to talk to each other by scattering photons amongst each other. And that will be sort of these photon-mediated interactions will be the focus of my talk today. So why would you want these sort of highly non-local structures of interactions? There are a few different directions one would like to go with this. One is that having any atom talk to any other can be a way of efficiently generating entanglement in a massively parallel fashion. And that's something that's already demonstrated for generating resources, for example, for enhanced sensing and clocks. Another direction is realizing certain actually models that, theoretical models that are written down on paper to describe systems ranging from condensed matter systems to quantum gravity actually feature weird non-local interactions. So I'll say a bit more about that later. And the third direction, though, is maybe you'd like to actually use your quantum system to solve some classical real-world optimization problem that can be mapped, and there's a wide range of problems that can be mapped to the problem of finding the ground state of an interacting spin system. And the idea is maybe if you can build that particular interacting system in the lab, you can use the physics use physics to steer it into its lowest energy state and solve that classical problem. Let me give actually just as a sort of starting point an example from this sphere of optimization. I actually always wondered, how do you map a real-world problem onto an interacting system that I could build in the lab? So here's a real-world problem that I encounter every so often, which is I go grocery shopping, and I have a set of n objects with specified weights, and I would ideally like to partition those objects into two groups that would balance a scale so that I can easily carry these two bags. For certain restrictions on the weights, this is actually an NP-complete problem. There's no efficient classical solution. As a physicist, if I'd like to maybe try to solve this problem, the first thing I am going to do is map this onto a system of interacting spins, so map this onto some kind of a spin problem. So what do I mean by that? If I have an object and I'm putting it in the white bag, I'll represent that as a spin pointing along plus z. If I put it in the green bag, I'll represent that as a spin pointing along the minus z direction. And so what I would like to do is to minimize the imbalance, I'll call that fz, which is some weighted sum of these spins, right? These are the weights of my objects. So I could minimize this fz, the imbalance, or equivalently, I could minimize the imbalance squared. And this looks like, right, this is a sum of products of these spins. It's basically something that says I have these various couplings that I call Jij that tell me how strongly the spins want to anti-align. And those, again, encode the weights of my objects. And in particular, if I draw sort of the graph of right, so it's an interacting system because I have products of these spins. And if I draw the graph of interactions, every spin is talking to every other. So if you'd like to be able to, for example, explore problems like this, some of the ingredients you would want is some way of encoding the spin, some non-local interactions, and some programmability of those interactions. Okay, so let me give you a flavor for how we realize these non-local interactions in a way that is mediated by light. So the basic concept is the following. Imagine I have an atom with two internal states. I'll call them spin up and spin down. And what I would like to do, if I want to use light to let them interact, what I can do is I can have this spin up atom flip its spin by emitting a photon, and I'll let that photon be absorbed by another atom, which in turn flips its spin. So what we've done here is we've basically converted a spin excitation into a photon back into a spin excitation that's somewhere else, right? And so we've generated, in this case, a spin exchange type of an interaction that's mediated by light. Now, of course, it's important that the photon not fly off in some random direction, but actually be absorbed by another atom. And so we've put mirrors around this system, and this allows the constructive interference to sort of build up for if a photon is scattered into this resonator, so between these two mirrors, and that enhances actually the probability that the emitted photon will be absorbed by another atom, as opposed to flying off in a random direction. And that general concept of having some sort of two-state system coupled to photons in a resonator appears in a variety of different physical platforms. Actually, it can be used to, for example, interface superconducting qubits with one another, or quantum dots. These systems on the left would use microwave photons. Solid-state spins can be connected to each other via optical photons in nanostructured waveguides, a number of different systems work with these cold atoms between sort of macroscopic mirrors that form the resonator. And which of these systems you would choose might depend on your preferred application, whether you're building a quantum computer, working on long-distance quantum networks, or perhaps tackling some problems in quantum simulation, or quantum measurement, for example, clocks or sensors made of cold atoms. So in particular, actually, one of the things I want to highlight about the cold atom system is the scalability. So there are experiments that work with 2 atoms individually addressed, and there are experiments that work with order 10 to the 5 atoms, and it's the same basic technology. And so that's kind of a neat feature of this platform. And so some of the things that have been explored with these platforms include harnessing these photon-mediated interactions to make a class of entangled states known as squeeze states. This is sort of some picture showing each atom is a spin. This blob is showing the collective magnetization of the system, but it's possible via interactions to actually suppress fluctuations in some particular quadrature of the magnetization, and that can actually then be used in a quantum-enhanced sensor or clock. Actually, you can flip things around and use atoms to manipulate the light field, and actually in the group of Dan Stamper-Kern, these types of systems have been used to make non-classical states of light. So those are some of the directions in sort of non-classical states for precision sensing. Another direction that's explored in a number of systems is simulating phenomena, let's say, from condensed matter physics. So supersolids have been realized in these atom cavity systems, topological states of photons, where the atoms allow the photons to interact. And there's work towards, for the condensed matter physicists, for example, studying spin glasses. So a few different directions in sort of condensed matter-inspired quantum simulation are being explored here. I'll touch on trying to extend this to simulating some phenomena from quantum gravity. So to say a little bit more, though, just to sort of put this in perspective, for me, these 2 directions of quantum control, can we make some useful entangled state, and quantum simulation are kind of 2 sides of the same coin. One of them is about making a particular entangled state that we know has a useful property, like I gave this example of squeezing these quantum fluctuations. And one of the neat things in this quantum control example is that even though this is some entangled state of 100,000 atoms, I've drawn you actually a picture of this state in spite of the quantum correlations that are present, which you might think would be hard. So these are sort of entangled states, but the form of the entanglement is in some way conceptually simple. On the flip side, in quantum simulation, the goal is to sort of have a model system that allows you to understand something about perhaps the form of interaction is simple to write down, but those interactions give rise to complex quantum correlations that make it impossible to fit a description of the system on a classical computer, and so you need to simulate it to understand what will happen. And so in this regime, where sort of it's too complicated to calculate what will happen, one of the things you might ask is there any hope of being able to sort of even have some visual representation of the quantum state in the way that I made on the left here? So I find these visuals useful often for understanding, what are the properties of the state. So I was actually intrigued when I learned about some ideas coming from quantum gravity for how one might be able to even start to have visual pictures of more complex quantum states. And the rough idea is that if I have a quantum system in one dimension, let's say. So I've shown that here as sort of a chain of sites. In this case, we'll connect them in a ring. So this is some quantum system that through interactions we might expect to have entanglement. And the idea is that in certain cases, there's actually a classical picture for sort of encoding the structure of correlations in the quantum system, where I describe this as having one additional spatial dimension. And in particular, this additional spatial dimension has a geometry, it might be curved, that captures something about the strength of correlations between different sites in the quantum system. So the idea is by adding one additional spatial dimension, this interior, this so-called bulk, can encode something about the structure of entanglement in the quantum system. So that, is an intriguing idea. And, when I heard that, I thought, well, I wonder, are there cases where one could sort of probe this type of a bulk geometry experimentally, either in some simple model system or in cases where it's not known whether such a picture applies, but perhaps you could learn in experiments about how to visualize these states. So, if you want to start to explore this, you need some starting point of a prediction coming from this holographic duality. And so one prediction that has been put forth has to do with what would a quantum system behave like if under this duality it is equivalent to a black hole. And the prediction is that, well, in black holes, any information that's initially information very quickly becomes effectively lost. But it's not actually lost. In the quantum system, what's happening is that it's becoming sort of hidden in complex correlations among the many degrees of freedom. And in order for a quantum system to be in this sense like a black hole, this process of the information becoming scrambled among the many degrees of freedom would have to happen exponentially quickly. And so if you'd like to study this in the lab, you can take a look at sort of models that are written down on paper for describing this process, and they look sort of strange. So for example, they might have particles that can hop in a completely non-local fashion, or they might have a weird behavior that is local but in a very strange geometry. So for example, models of billiards on a tree graph were proposed for explaining this phenomenon. Okay, so can we study anything like this in the lab? Let's start with this type of idea of having particles that can hop in a non-local fashion. I don't know how to do that with massive particles, but I showed you before that in these experiments with atoms talking to each other with the aid of photons, you can have spin excitations hop between the atoms. And the spin excitations can hop in essentially a non-local fashion because light travels, for our purposes, essentially instantaneously. And so light will carry these spin excitations over long distances. To do this in a controllable fashion, the experiment looks something like this. We have a control laser that we use to essentially, when we turn this laser on, we drive a process where an atom absorbs a photon from the laser, emits a photon into a resonator while flipping its spin, and another atom absorbs that photon and flips its spin in turn. So that ought to be able to generate processes where spin excitations hop. In the lab, it looks something like this. In this simplest case, I just have kind of a cloud of atoms a few hundred microns long. It's optically trapped in a standing wave of light. And here's some experiment where we initiated some spin excitations in a particular region of the cloud and kind of watch where they go as a function of time. One sees them hop over here and hop back. If you look at any fixed time, you see some oscillations showing that there's some quantum coherence in the system. The fact that they suddenly sort of hop from A to B, you might kind of wonder, why do they suddenly show up here and not propagate outwards? And it turns out that one can understand all of this just by knowing the local density of the atoms and the local intensity of the light field. And in particular, in this case, the light intensity was strongest here. But it kind of highlights the non-local character of these interactions. But so far, the structure of the interactions is just dictated by what is the local intensity of the light field. We'd like to be able to go beyond that and have some control over the spatial structure. And perhaps also have control over a few other aspects of the interactions, like do I have these flip-flop interactions where the spin excitations can hop, or do I have so-called Ising interactions, what I showed before in our optimization problem, where the z components want to either align or anti-align, and maybe I'd like to control the sign of the interaction. Are they ferromagnetic, the spins want to align, or anti-ferromagnetic, do they want to anti-align? So let me start by giving a flavor, actually, of this sort of controlling the form of the interactions. And then I'll come back to the spatial structure. So actually, just in the simplest case, every atom talks to every other one. I can actually sort of write down a description of the system in terms of some large spin that is weighted by the local intensity of the light field. We wrote down a large weighted spin like this before. And then the form of the interactions, though, turns out to be one thing that we can already start to tune in this system. And it turns out just by actually adjusting the orientation of a magnetic field relative to the axis of the resonator, we can smoothly tune between the case where I have so-called Ising interactions, the Z components want to align, or these what I call XY interactions, which is the spins want to exchange. And just by a laser frequency, we can also control, is it a ferromagnetic or an anti-ferromagnetic interaction. Just to give a bit of a flavor of something you can do with that, here's an experiment where we measured the magnetic susceptibility of this system with either Ising interactions or XY interactions, and notice the neat feature so this is as a function of some applied transverse field. There's a neat feature that these two plots are mirror images of each other, which says that having Ising interactions of one sign is equivalent, actually, to having these spin exchange interactions of the opposite sign. You might ask, sort of, why is that? And it turns out, why is it that having the spins want to align along Z is the same as wanting to have them anti-align along X and Y? And it turns out you can actually understand this by maybe drawing kind of a picture of the energy as a function of, let's say, the Z component and the X component of the spin. They look different for these two cases, XY interactions of one sign, Ising interactions of the other. But they actually look the same if you restrict yourself to the case where all of the spins started aligned and I have a fixed total length of the spin. So in the experiment I showed before, that was roughly the case. These two systems looked equivalent. But if you actually allow for the length of the spin to change and go into the interior of this kind of picture here, where I vary the length of the spin, then there's actually a key difference, which is that in the case of these Ising interactions, there's no energy penalty to shortening the length of this total spin, to letting the spins anti-align. But in this case of the XY interactions, actually there's an energy cost to sort of moving inwards on this sphere. So it turns out that this is actually a useful feature, because it means that if you have the ability to engineer these spin exchange interactions, it can actually protect the spins against dephasing. So this is an experiment where we sort of looked at the dynamical response of the system to an inhomogeneous magnetic field. This is a non-interacting system. As a function of time, one sees a sort of spiral texture evolving, which is the spins dephasing as a function of position. But if you turn on these XY interactions, the phase is completely uniform. The spins stay aligned. So there's no phase winding across the cloud, whereas again for Ising interactions, the phase simply winds. So this is kind of a feature that was proposed by the group at GILA as a way of sort of harnessing interactions to protect the coherence of the system. There's an energy penalty in one case to making the spins become misaligned. And that actually can have implications for protocols where one wants to use the light to generate entanglement. You can do this potentially in a more robust way if you harness this tunability to generate spin exchange as opposed to Ising interactions. So that's kind of one feature of something we were able to explore, harnessing some of the tunability of the interactions. I'd like to get deeper into programmability of the spatial structure, but at this point I want to actually pause and ask whether there were questions on things I said so far. I saw some things in the chat, but I don't know if there were questions.
The things in the chat were all just messages from Elizabeth about. Yeah.
Okay. All right. Okay. Great. So then I'll continue. Okay. So I kind of motivated some of this in terms of this could make the system more robust if you want to use the light to generate entanglement. I also gave some examples before that this has been done, but I thought I would just give a flavor of sort of a new way that one might actually generate entangled states in the system that we've been exploring in our lab. And that's actually requires me to say one more thing that I didn't say before, which is each of our atoms in our experiment is actually a spin-1 system. So we have 3 internal states. I'll call them -1, 0, and 1. And we can, for example, do an experiment where we initialize all atoms in the 0 state and turn on interactions. And if the interaction is this spin exchange type process I mentioned before, where one spin can flip up when another flips down, this actually allows you to take two zero atoms and form a pair of +1 and -1 atoms. And for every +1 atom, you need to get a -1 atom. If you do this type of experiment, actually what you see is this is sort of 100 repetitions of this experiment. The first thing you might, each time I plot to show a picture of the atoms in the three different states, there are some large fluctuations, but whenever there's a high population in the -1 state, there's also a high population in the +1 state. And so this is kind of a signature of a process that, in our understanding, gives rise essentially to correlated atom pairs. It's familiar. It's sort of similar to processes that have been observed by direct collisional interactions. Some of the pioneering work on this type of physics was actually done in the group of Dan Stamper-Kern. And since then, these interactions were applied to generate states where one has precisely the same number of atoms in up and down, but no idea which atom is in which state. So that's actually a highly entangled state that has applications in enhanced quantum sensing. One of the things that the ability to generate these interactions with light could allow you to do is to start to actually control the spatial structure of the correlations. And so in order to sort of cleanly study that, we trap our atoms in our most recent experiments in an array of small ensembles. And the dream is ideally to be able to sort of program which of these ensembles talks to which other one. So ideally, we would love to be able to dial in any graph of interactions, but we'll modestly actually focus on controlling the interactions versus distance in this array. Right, so in the simplest case, every atom would talk to every other. If we want more control, the first thing we want to do is actually break down that all-to-all connectivity. And the way that we do that is by applying a magnetic field gradient across the system. So in the presence of this gradient, if we study this pair creation process, the formation of these +1, -1 pairs, the magnetic field gradient means that there's an energy cost to forming these pairs at a distance, but on the same site, that process conserves energy. And so if we measure the correlations between the number of +1 atoms on site I and the number of -1 atoms on site J, you'll see correlations appearing kind of on the diagonal, so which shows that the interactions are local. If we, however, add a second laser frequency to our drive field, then we can actually, because there are two different photon energies present, we can actually bridge the energy cost of creating these +1, -1 pairs at a given distance. And therefore, we can see in this correlation plot correlations off the diagonal at some particular distance set by the frequency separation between these drive fields. So now this generalizes as I change the frequency at which I modulate the laser that's driving the system. The distance at which I will observe these correlations tracks. And there's very fine control. So you can really decide, do I have interactions at a distance of 9 sites or 10 sites or 11 sites, just by dialing in the modulation frequency. So then that suggests actually the modulation waveform of a laser is quite easy to control. So then we can go beyond this and ask, can we get more complicated structures of interactions or richer structures of interactions? So one trick you can play, it turns out, is if I take a given waveform and on top of it add a faster pulsing, I can think of this as adding in sort of higher modulation frequencies that connect the ends of the chain. And so whereas if I have just this smooth, continuous waveform with which I drive the system, I'll get interactions at one particular distance. If I additionally pulse this waveform, I'll also get interactions at the length of the chain minus that distance. So you effectively convert an open chain into a ring. That starts to hint at the fact that kind of the geometry of this interaction graph doesn't have to be the same as the physical geometry of the system that I have in the lab. And so, I kind of told you this is a ring, but we can even kind of from more in a black box way really try to reconstruct what is effectively the geometry of the system. So, my students pointed out, well, actually just from these measured correlations, let's see whether we can find some kind of best fit geometry of the sites to explain the measured correlations. By adopting some ansatz that the correlations decay with distance, you ask sort of what is the best fit geometry in 3D to explain what we measure, and in this case it's a ring. And it has a little bit of a kink, it's an experiment, it's not perfect, but it's a pretty clearly a ring. And I should emphasize they've actually drawn in here there are order n squared possible bonds. All of them are actually drawn in this picture. they're shaded according to the strength of the correlation, and the ring pops out. So now you can extend this to some other interaction graphs. In the simple case where I have open boundary conditions and interactions at a distance of 3 sites, I guess I can now make it a problem for the audience in your mind to ask, what is the effective geometry that's going to come out of this? Okay, so then we check, and what we see are actually, so this looks like 3D coupled chains. That kind of makes sense. I could have drawn the interaction graph in a slightly different way. We can be fancier and say, let's have nearest neighbor interactions, periodic boundary conditions, and while we're at it, let's also add some connections across the ring. By the phase of the modulation, we can decide, are the interactions ferromagnetic or antiferromagnetic? For fun here, we made them antiferromagnetic across the ring, measured some correlations, and again, you can guess what is the effective geometry that pops out. It's a Mobius strip. So I think this kind of highlights some of the flexibility of the control here of interactions. By the way you can understand these red and blue bonds is that in this picture of the ring, the spins are kind of winding once around the ring. Yeah, and so now you can play with different waveforms and watch what geometries come out. You could make it a cylinder without a twist instead of the Mobius strip with the twist. You could make a fully antiferromagnetic ladder that is of interest for studies of frustrated magnetism. And indeed, there are a number of different directions that we think this can go, from exploring spin dynamics in exotic geometries, accessing non-trivial topological features ranging from sort of the twist of the Mobius strip to perhaps the winding has some topological aspect. Studies of frustrated magnets, and in particular the fact that the sign can change is of interest for studies of spin glasses. So there are a number of different directions this can go. One of the things we're particularly interested in is, some of the geometries I showed, there are other physical systems where you could realize something like a 2-dimensional ladder. But can you use this highly non-local interaction to do some things that you really can't do in any other way? So that brings me back to this idea of building perhaps some toy models for quantum gravity. And I have to admit, I myself don't really know much about gravity, and so I was very fortunate to have the opportunity to collaborate with some people who know more than I do, one of whom was Steve Gubser, who tragically passed away in a climbing accident a couple of years ago, but taught me quite a lot before that. And Steve was particularly interested in understanding what is the mathematical description that underlies the reality that we experience as smooth space-time, but which fundamentally, in all likelihood, we think should be discrete based on the fact that quantum mechanics is there and there's a Planck length, right? And Steve actually formulated a version of this holographic duality that is based on having a system where the sites live on the leaves of actually a tree graph. And the idea here is that this tree graph, you can think of as kind of a discretized version, a discretized model for a curved space with gravity. So why is it curved? So on the right, I drew kind of a version of this graph wrapped into a ring. The circumference here is n sites, but the depth of the tree is only log n sites, right? And so that means there has to be some curvature here in the interior. So, maybe if you can study quantum mechanics in a tree graph, you can start to explore some ideas from quantum gravity. There's a toy model that we had sort of written down on paper and in this theoretical paper that has the neat feature that it in principle should allow you to tune a system between 2 very different geometries, one of which is just a linear spin chain, and the other one is something where the sites are leaves on a tree graph. Okay, and the basic idea is imagine you could have interactions at distances that are powers of 2, but you can control whether those interactions shrink with distance or grow with distance. So if they shrink with distance, it's not so different from having just nearest neighbor interactions. But if they grow with distance, there was the sort of conjecture is that the system should behave something like the sites being leaves on a tree. And actually, these are 2 radically different geometries, and the other conjecture is that at the sort of at the intermediate point between the 2, everything should be sort of strongly connected to everything, and this might give rise to fast scrambling. Okay, that sort of black hole-like fast scrambling. So now we thought, let's just see, can we realize this tree-like geometry in the experiment? And so here's an experiment where we just programmed in those interactions at distances that are powers of 2. and looked at the measured correlations in our system. So here's a plot of correlation as a function of distance in our physical chain of atoms, of small atomic ensembles. The correlations show some kind of weird non-monotonic behavior. And if this system is really behaving like the tree graph, there's actually, there should be actually sort of a better way to think about the structure of correlations in the system. And to understand that, I should say something about the way this tree graph is constructed. Roughly, the idea is that one goes left or right on the tree, depending on sort of the least significant bit of the site number in the actual physical geometry. Each step down the tree, one looks at a slightly more significant bit. So the leaves on the tree are in a scrambled order compared to the physical positions that I get by reversing the order of bits in the site number. And if you actually plot the correlations as a function of the tree index, the position on the tree, you start to see some structure in this plot, and it has sort of even a hierarchical block structure that matches the hierarchical structure of the tree. And if you plot the correlations as a function of the effective distance on the tree, the correct notion of distance on the tree, they smoothly decay. So that's some evidence that perhaps we're starting to explore this tree-like geometry. But we thought, can we also do this sort of black box reconstruction? And the challenge to doing the black box reconstruction here, potentially, is that unlike these other graphs I showed you, like the Mobius strip, in the tree graph, actually only the leaves of the tree are really physical sites. And the rest of it is just some construction that is this bulk that's supposed to explain the effective distances between the sites. Okay, so here's sort of an analysis where my students said, well, let's find the best fit positions of the sites in 2 dimensions to explain the strength of the correlations between them. But then let's also draw connections between pairs of sites that are most strongly correlated, and adopt a coarse graining procedure where we then, when we connect 2 sites, we treat them as one, and then we look again which sites are most strongly correlated. And when you adopt that sort of sequential procedure of coarse graining and drawing bonds, what shows up is actually precisely this tree. So again, this is not something where each vertex of the graph is actually an atomic site, but something where the system of physical sites lives on the boundary, and this tree is really kind of this representation of the bulk geometry that encodes something about the structure of correlations. Okay. And just to sort of illustrate that point in one other way, you can ask sort of, let's consider different ways of cutting the system in half and asking how correlated the 2 halves are. So you could cut according to the physical geometry, and the strength of correlations is shown here in blue, and the 2 halves are sort of only weakly correlated if I built sort of the system that's roughly a linear chain where interactions decay with distance. Alternatively, if interactions grow with distance, I actually have to cut according to the tree. Those are the green points here, for the correlations to be as low as possible between the 2 halves. And if you sit right at this point in the middle between these 2 geometries, there's actually no way of cutting the system so that the 2 halves are weakly correlated. And that's sort of some indication that everything is now strongly connected to everything, and perhaps that is in fact conducive to this fast scrambling behavior, and that's an interesting direction one could explore in this system. So I hope I've illustrated to you that we have quite a range of knobs here on our function generator for programming the interactions in our atomic system. We can control the sign of the interactions. Is it ferromagnetic or anti-ferromagnetic? The form of the interactions. Do we have these kind of flip-flop processes or Ising interactions? But also really the graph of the interactions, the spatial structure, to realize some rather exotic geometries and topologies. And we're eager to take this toolbox and apply it in a number of different directions, ranging from kind of further exploring these simulations of models inspired by quantum gravity, to exploring topological aspects that, in particular, I showed you control over the signs of interaction, but even complex hopping parameters that are used to generate effective magnetic fields for the spin excitations are something that could be explored. We would love to engineer specific interaction graphs that could allow for studying, can you harness the quantum system to solve some classical optimization problem? or models of frustrated magnetism inspired by condensed matter physics. And lastly, we would love to actually directly measure entanglement in the system and ask, are these quantum correlations useful as a resource, perhaps for enhanced sensing with spatial resolution, or for some computational applications. So with that, I'll just thank my team, and in particular, Eric Cooper, Avakar Parawal, and Philip Kunkel have been essential to the latest experiments I showed, building on really important prior work by Emily Davis, who's now a postdoc at Berkeley, and Greg Benson, who also played a key role in some of the theory connected to toy models for gravity. So with that, I will thank you all for listening and take any questions.
Thanks so much, Monika. Yeah, so if anyone has questions, then just either raise your hand or just sort of shout, and yeah. Thank you very much, Monika, for a really great and awesome talk.
Great.
Maybe I should have said we should clap.
So are you moderating?
Yeah.
You moderate?
Yeah, Dan Stanford Kent, you want to?
It's a very inspiring talk. Is there a stage at which can we just keep interactions to fill up this entire network of interactions, or does the cavity spectrum sort of get too crowded? Is there like a limit, sort of an information bottleneck on how many links you can connect?
That's an interesting question. So there are definitely some sort of at least technical limits. I would say, so one thing I can say is that we have already taken advantage of kind of the full dynamic range for these chains of order 20 sites, in the sense that we have had connections sort of at a distance that's the length of the chain, and also between nearest neighbor sites. And so in some sense that corresponds already to, for this system size, I don't think there's an issue of spectral crowding. That said, we had to take some pains one needs to be sufficiently far detuned, one needs a detuning of the drive laser that's far enough from cavity resonance that you can fit this range of different frequencies in with approximately constant detuning. So it's definitely sort of, there is a parameter regime where things work. Right now, I would say, in terms of kind of how much you can scale this, I would say, I think for a system of something like 100 sites, that would be reasonable, sort of limited by the focused region of the Rayleigh range of our cavity mode, and having a reasonable kind of separation between the sites. The other limitation in terms of the complexity of the interactions is that, in some sense, the way that we get such control over the interactions, instead of having everybody talk to everybody else, is we're kind of canceling out the interactions we don't want by letting kind of the spins dephase in a gradient. But there's something where arguably that's not so efficient, in terms of they still scatter some light that, as you know, can cause decoherence. And so in some sense, I would say the more complex you want to make the interaction graph, the higher a cooperativity you need, so the figure of merit for the coherence of the interactions. And so we do benefit from having many atoms per site to boost that figure of merit.
Anastasia, Leon, do you want to ask a question?
Oh, yeah, I was just wondering, it was just a quick question about one of the graphs that you had, I think on the bipartite kind of correlations.
Yes.
So I was just wondering, so how are can you remind me how you decide to make the physical or the tree cut? Because I would have expected, if you're right for S, you kind of have these two discrete domains of where it's like a physical line if it's less than 0, but this tree structure if it's greater than 0. So I was wondering, like, how do you make the tree cut in like a system that has these, like, has more of a like just in a line like geometry?
Yeah. So first of all, I should explain that all of this about cutting is just done in post-processing of the data. And there's this fancy term bipartite correlation, but really all we're doing is we're taking half of the spins and treating them as one larger spin, and the same for the other half, and asking what is the correlation between those two quantities. And so this is all done in post-processing. And so essentially, we can decide how we group the sites, and the 3 different curves here are, right, and we can do that irrespective of what interactions happened before we do our analysis. And so the blue points are really, we treat the right half as one larger spin and the left half as one larger spin, and we ask how correlated those are. And the green is just, instead, we first reorder the sites according to their position on the tree and do that same thing. And the key point here is that depending which form of interaction you have, the sort of right way to cut the system, and by right, I mean that the correlations between the two halves are weak, right? That's going to depend in sort of the way that you would expect. And then the last thing, we've sort of considered really all possible cuts. So the physical cut, the tree cut, but also any other bipartition of the system, and checked what is the optimum for minimizing correlations between the two halves. Did that answer your question?
Yeah, thanks.
There's a question that was sent to me earlier in the chat, actually, which is, what type of light are you using for these experiments, and was there a reason this was chosen?
What type of light?
I assume it means frequency.
Yeah, first of all, I guess, what comes before choosing the light is choosing the atoms, and for various reasons, we work with rubidium atom. It's basically technical convenience, and partly convenient laser wavelengths. So the wavelength that is resonant with the transition we use in these rubidium atoms is 780 nanometer light. And that is a wavelength where there are convenient diode lasers available. So that specifically, well, actually, there's more to this story. So I don't know how technical the person wanted me to get in the answer, but we start with a laser that's at 1560 nanometers, which is something where there's narrow lasers commercially available. We frequency double it. We have a narrow line width laser at 780 nanometers. And then we actually phase lock another laser to that to get the power that we want to drive the interactions, and that's a diode laser. So, but maybe what I can add is all of this modulation to control the interactions is very, at least to me, it seems simple. Maybe the students who actually do it will disagree, but it's literally just intensity modulating the light with an acousto-optic modulator.
It's Stress. Do you want
to myself? Hi. Oh, that was just a wonderful talk. My gosh, you got me going. Can you go to the slide where you have with the first slide where you had the diagonal coherence? Yes. Well, not actually.
Sorry,
actually, go back to right there.
Mm-hmm.
No, back.
This one.
No, one. Yeah. Okay. No. Before that. This is later.
I'm not sure.
Keep going back. Keep going back. Keep going back. Oh no. That's too far. That's too far.
If you ask your question, maybe I'll find the right.
Yeah. Okay. Yeah. So you had one correlation across the diagonal like this, and then you had 2 side pieces like this. I'm assuming they're aliases.
Oh, I think I know what you mean.
There.
This is the plot.
Yes.
Great. So actually we wondered about this. So why are there higher order correlation peaks? And there are 2 things you might imagine. One is maybe we have some anharmonicity in our drive field, and so our interactions are actually showing up at longer distances. Or, so that's one possibility, but my students assure me they were very careful to rule out any anharmonicities. So the other, but actually I'll show you some data. The other thing is maybe the interactions, these are correlations, right? So maybe first there were correlations at a given distance, and then they spread to longer and longer distances. And actually, I can maybe just, can you still see my slides?
No.
Just closed.
No, it's a great picture of you.
There's a picture of me. Okay, wait. Let's see if I can. Let's see if I can get this to show up again. Okay, share screen. Just share it again. Can you see this?
There you go. Yes.
Yeah. So actually, one of the things we can do is look at how the correlations evolve in time. And particularly, this is correlations between the x components of the spins, and you can really see kind of, so this is distance and time, and you can see the correlations kind of spreading over time to more distant sites. Another way to think about this, you
They're
can Fourier
hopping.
transform this and look in momentum space, and you can kind of see peaks growing and it's narrowing in momentum space.
Yeah. But it looks like they're hopping in the first one. It skips every 3-1. Bump, bump,
Oh yeah,
bump,
and this is
bump,
because we
bump.
turned on interactions at a distance of 3 sites, and so over time you see correlations at 3 sites, 6 sites, 9 sites, and so on.
Okay, so then another question. Next question that I have, the second question, the last question I have is like I'm wondering about. I mean, at one stage you used frequency modulation. Is that correct? Was it?
It's actually amplitude modulation.
Oh, okay. Okay. So,
and it turns out one way to think about that is the spins are kind of rotating in this gradient. And what we're doing, you can almost think of it as the intensity goes up when spins at a particular distance are aligned with each other. And those are, that sort of sets the distance at which the interactions are on.
Yes, I mean that's basic. I was going to suggest some things, but some other kinds of modulation, like phase modulation.
Maybe this could wait until after.
Oh, but here's the question: do you how do you get the more structured modulation? What do you do for the frequency to make the more structured forms that you have? That was my question.
Yeah, so it's always just adding sort of multiple modulation frequencies. So it's a more complex waveform, gives you more complex interaction graphs.
You just AM modulate it.
But it's all, yeah, exactly.
It's complicated things. Okay.
Yeah.
Rob,
thanks.
Yeah, I was curious. You have the analogy of your function generator. So I was wondering how close to an arbitrary waveform generator is your function generator? I.e., how close can you get to arbitrary connections and arbitrary graphs? And sort of related, how controllable is your system?
Yeah, so in terms of how close to arbitrary, the key restriction, I would say, so far is that these interactions are translationally invariant. Now, that's not to say we can't make things that aren't translation invariant, because, for example, there's no reason the sites need to be physically positioned in an ordered array. Or conversely, actually, our gradient, we have this linear field gradient that sort of gives the translation invariance. That doesn't have to be linear. So one could go beyond that, but I would say what's very natural and what we definitely can do in an arbitrary fashion is to make any dependence of the coupling on distance for this spin exchange type of coupling. So for these XY models. And that can include the sign or even the phase of the coupling. Does that kind of answer the question? Yeah.
Say how Dai. You next.
Hi. So it looks to me that you can easily simulate a 2D system using the 1D chain. For example, if you have 100 atoms, you have interactions every 10. Between site 0 and site 10, site 1 and site 11, and the nearest neighbor interaction. Is it a 2D lattice? Do you have plan of simulating 2-dimensional physics? And is it possible to simulate fermions in this platform?
Yeah, so for the first question, for 2-dimensional physics, definitely that's possible. And I already kind of gave an example of this ladder type of geometry. Now I think something that we would think about is this something you can't do in other systems? So arguably, some of these pictures I showed of positioning atoms in tweezers to make a particular 2D geometry might be a more natural approach for some 2D models. So I think what's kind of neat is that you can easily do these things like periodic boundary conditions, add some longer range couplings. Yeah, but it's very true that we can make things that are 2-dimensional. There's not a natural way to study fermions. These are spins, and I should mention that also in everything we're doing so far, it's not just sort of a single spin on a site, but it is this sort of collective physics of many atoms. And if you want to push it to something that might be more sort of, you're more used to thinking about theoretically, where there's like a single spin half or single spin 1 on the site, that takes some work on pushing up the strength of atom-light interactions.
Thank you.
Mm-hmm.
So maybe I'll ask a question myself, which is, so if you're really wanting to get something more like the SYK model or something like that, then you not only need to have all-to-all couplings, but you need to have sort of 4 local interactions or more than two atoms speaking to each other at a time. That seems like it could be very hard to do using light mediated stuff. Is that accurate?
Yeah, so maybe just first as a comment, I'll say that I don't think of the main goal of this as realizing SYK exactly, but maybe exploring other things that aren't SYK. But I think in principle, you could think about what processes you can generate at higher order in perturbation theory. In practice, the issue might have to do with kind of how does the strength of those types of interactions scale compared to dissipation rates, and my instinct is that it's not so favorable. There are some ideas for making four-body interactions in somewhat different ways, that, for example, one has a central spin that mediates interactions between four other spins. That's been thought about in Rydberg systems, but maybe there's some analogy that could be explored here.
Any other people waiting to ask questions? Now is your time if you're feeling shy. Okay, maybe I will. Oh, Anastasia has another question.
Oh, yeah. I was wondering if you might give an example of, you mentioned kind of the possibilities for kind of simulating quantum gravity situations. I was wondering if could speak a little bit more to the possibilities for that, or what would you be looking at?
Yeah, I mean, I think one question is, can one look more closely at the dynamics of some of these models and ask, I said there's some sense that in one model we showed everything is kind of strongly connected to everything else, but not in a simple, but in a way that might be conducive to fast scrambling. And so that's something that would be neat to explore in this system. But also, to me, I think this idea that in one kind of simple toy model, we did this reconstruction of a bulk geometry that explains the structure of the correlations. To me, an interesting question is, would it be useful to adopt that type of procedure with maybe other systems where you don't sort of already kind of know what should pop out, but maybe could learn something. But I'm also open to, those are kind of some directions that I think one might go. But also I'm really open to hear from theorists about what might be cool to do with this toolbox that we haven't thought about yet. So.
Thanks.
Okay, any other questions? Okay, I might ask one more question then, actually, which is, so in classical computing in the sort of early days, there were various analog simulators of various kinds that we used and were fairly successful, but then at a certain point, digital computing just outstripped everything. Do you see the same thing happening in quantum computing eventually down the line? And if so, I guess how long off? Yeah.
Yeah, that is a good question that I don't think I can claim to. I'm hesitant to try to give a very confident answer on that. But what I will say is that I think sort of right now, we're at a time where there's been really kind of remarkable advances in control in a variety of different platforms and coherence, where to me, sort of the exciting question for now is, can you already use these systems to compute for certain classes of problems that naturally map onto the hardware? Because my sense is that we're still a ways away from a full error-corrected quantum computer, but that there are particular problems that really map naturally. Actually, this number partitioning problem, I told you one way you might encode it. We've actually been thinking, we have a theory paper on ways you could address that problem in systems that are central spin systems, for example. Just naturally maps onto that class of system. And more broadly, so this, to me, sort of there's this exciting question of kind of what are some near-term hardware efficient algorithms, even if in the long term there's ultimately a universal quantum computer that's error corrected and that becomes obsolete. I think it will have been an important step along the way. So. Lastly, tying that to the previous question, I know there are some ideas coming from quantum gravity about how to do error correction, and I would love to learn more about that and whether there are sort of some of these tree graphs actually have some connections to that, and that's something that I would love to learn about and ask whether we can explore it.
Awesome. Okay, any more questions? Otherwise, maybe we should end the recording and just go to sort of some informal chatting. But anyone who wants to stick around and chat to Monika is very welcome to do so.
Thanks again so much for the invitation.
No, thank you so much for coming. It's yeah, great to have you talk. Okay.